So with those ideas from the double replacement reactions, we're going to expand forward to do all the types of reactions. You're going to need your notes about types of chemical reactions because they're going to be the thing that's going to help you here. So you may want to grab those and put them next to you. When you need to predict the products for a chemical reaction, step one is to look at where you start and decide what type of chemical reaction you have. Is it combustion, combination synthesis, decomposition, single replacement, or double replacement? And that's where your notes are going to help you. Knowing what kind is going to give you kind of a general pattern to follow when you do this. Then, based upon the type of reaction and kind of the pattern of reactant becoming product, you're going to write the formulas for the products. We have to, along the way, watch out for ionic compounds, making sure that they add to zero, and watch out for diatomic elements. And when something becomes just an element, make sure you check your periodic table to see if it's diatomic. Remember, we colored all the boxes for the diatomic elements with some kind of bright color. It makes them relatively easy to identify. After you have good chemical formulas, you're going to balance the equation, and then you're going to write the word equation. So we're going to do two examples together and then turn you loose to practice with the rest of these. The first one is another double replacement, except I've taken away all the scaffolding and the boxes and stuff that help you do this. So we have to remember the parts and pieces for doing double replacement. So thing number one is identify what you have. I have lead ions, but lead is a transition metal. I have nitrate ions, which is NO3 minus. And if the lead got together with two NO3 minuses, that must make the lead a 2 plus. And then I have potassium ions and iodide ions. Double replacement is a partner switching situation. So I trade the partners and I use my fill the box to get good chemical formulas for my new compounds. I have lead 2 positive and I minus, which means it takes 2 I minuses to get the job done. So one of my products is PBI2, and then I have K positive and NO3 minus. That's +1 and -1. So we have KNO3. And we knew to do that because we had looked at this and we had determined that this was a double replacement reaction. Now we do our balancing. Since I can find a nitrate here and I can find another nitrate over here, I can leave those together and just track my nitrates if I want to, but you're welcome to split them up if that makes you feel better. So we have 1 lead, 2 nitrates, 1 potassium, and 1 iodine. 1 lead, 2 iodines, 1 potassium, and 1 nitrate. So to get my 2 nitrates, I'm going to use 2 of those. And in doing that, I now need 2 potassium, so I'll stick a 2 there. That fixes the potassium and the iodine. So now I have it balanced, and I'm just going to write my word equation here. My word equation is that lead to nitrate, need that Roman numeral because it's a transition metal, plus potassium iodide becomes lead to iodide plus potassium nitrate. Onward to the next one. So we need to look at our two reactants here. We need to make a decision. What type of reaction is it? So look in your notes. This one's a combustion. Combustion is actually the easiest type of reaction, and yet for some reason it causes more problems than any of the rest of them. These all follow exactly the same pattern. These all follow the general pattern that you have some fuel, okay, plus oxygen, yields carbon dioxide, plus water vapor. Which must mean that the products here are CO2 and H2O. Combustion reactions are literally fill in the blank. You just keep changing what's in the fuel box. Everything else stays the same. We know this from our fire triangle. Fuel plus oxygen is what it takes to burn, and it makes carbon dioxide and water vapor when all is said and done. People make this one more difficult than it needs to be. I think they just don't want to accept that everything else could possibly be the same. That adding oxygen and making the carbon dioxide and water is just the same every single time. These are your CHO reactions, and we always balance them in that order. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. So I have 2 carbons, 3 hydrogens plus 2 hydrogens plus 1 hydrogen, 6 hydrogens, 1 oxygen there, plus 2 more oxygens there for a total of 3. On the other side, my carbon dioxide has 1 carbon and 2 oxygens. My water has 2 hydrogens and another oxygen for a grand total of 3 on the oxygens. We balance them in CHO order. To get my carbons up to 2, it's going to take 2 of those. So that's 2 carbons. My oxygen has become 2 times 2 for 4, plus an extra 1 from the water for a total of 5. Now we balance the hydrogens. Need to get to 6, so I'm going to stick a 3 right there. That gets me to 6 hydrogens. Oxygens is 2 times 2 for 4 from the CO2, and another 3 from the water for a grand total of 7. Initially looking kind of bad because I need 7 and they're coming in pairs. But this time we're lucky enough to have an odd oxygen in the middle of this compound. So I really just need to get 6 of them in addition to that. So in this case, a 3 right there gives me 1 oxygen in the fuel, 6 more from the incoming O2s, for a total of 7, and I'm balanced. And then for the combustion reactions, we're just going to have to give you a name for the fuel. They're named by a different set of rules. This fuel happens to be called ethanol. So ethanol and everything else is always the same on a combustion reaction. Ethanol plus oxygen yields carbon dioxide plus water vapor. You can take it forward from there.